Hello, everybody, and welcome to WCA Physics class. Miss Peachy again. And here we are looking at your lesson on projectile motion. And so this first lesson, all we're going to be looking at is projectiles that have been launched at a horizontal. And what that means is that they have no vertical component of velocity when they first are launched. I know that can be kind of tricky to understand what we mean by that. So think of it this way. If I just push something off of a table, I'm pushing it horizontally and I'm not throwing it up or throwing it down, right? It's only moving horizontally. And as soon as it falls off the table, gravity takes hold and it starts to move then vertically. That's horizontally launched projectiles. If instead of just pushing it off, I actually was standing on the end of a cliff and I threw something off, I am at that point giving it both a vertical component and a horizontal component. Because I'm not just throwing it out, I'm throwing it up and out. And it follows a nice parabolic path. And then you would have a object launched at an angle, which we're not doing yet. That'll come later. Okay, so these are objects that start off just moving horizontally and then they fall. So when we do that, there's a few things that kind of helps to simplify everything. So first, let's look at our scenario. We have this instance where we have a cat that's sitting on the floor and an orange is rolling to the edge of a table and it's going to fall. And we really just hope the orange doesn't bonk the cat in the head. So we want to know how far that orange is going to go. Where is it going to land? Now, the first thing you need to know is as that orange is rolling, it has a horizontal component to its velocity, v sub x. That stays constant the entire time the orange is falling. Whatever the velocity is of the orange in the x direction when it leaves that table's edge will be the same as the velocity of the orange when it in the x direction when it reaches the ground. What changes is the velocity in the y direction. The velocity in the y direction when it's right here is 0. It's not moving down at all. As soon as it crosses over the edge of that table, it starts falling down and it starts picking up velocity. So it's going to speed up in the y direction faster and faster and faster. Remember that velocity is a vector. So as a vector, we can break it down into its x and its y components, right? So if we have a tabletop and we look at the velocity, at any point we've got two components to the velocity. We've got its x component and its y component. Right here on the edge of the table, it literally only has an x component. It's got the velocity in the y component is 0. At any given point along its journey here, the x component stays the same. They don't really have the y component to put gravity on here. But the y component of velocity is increasing. It just keeps getting bigger and bigger and bigger. Okay, so just kind of keep that in mind that we need to break this down into components. Because whenever we're dealing with a vector, we can't just solve the problem. We have to solve the x part and then the y part. So what we're trying to figure out here is how far it goes in the x direction. We are trying to figure out where does it land. So this is what we're looking at, and that is our delta x. That's the change in displacement in the x direction. As we move on, it gives you, in the next slide, it's going to tell you, or maybe it does in this slide, what the y direction is. It tells us that the table is 1 meter off the ground, so we have that. So our delta y is 1 meter. Our delta x is an unknown, okay? The other thing it tells us here is it's going to tell us, let's just kind of clear that off of here. Here we go. In the next slide, it's going to tell us how fast the orange is rolling. Remember, that's only in the x direction because it's only rolling horizontally. So our v sub x is 3 meters per second. And since v sub x is the same, no matter if it's at the beginning or at the end, it's always going to be 3. It's not going to change. So v sub x initial is the same as v sub x final. Now I've taken a screenshot. Actually, I took it with my phone and I emailed it to myself and I put it in here. But this is a picture from a textbook that we'd used up until like 2 years ago here at school. And I keep it because I like some of the stuff in the textbook a little better sometimes than the stuff in the lesson. And this is one of the instances where I think it's organized very well and makes it easy to understand. So you can see in this screenshot here, and let me zoom in just a little bit to make it bigger, that it's showing you that if you have a horizontally launched projectile, and this is true only for horizontally launched projectiles, that the v sub x initial is equal to the v sub x. It is constant. It's the same. It's not going to change. Now, what the other equation that they give you here is how do we figure out the change in position? Well, that's just velocity times time. We're just manipulating that equation. Normally, we have velocity as distance over time or displacement over time. Well, displacement is velocity times time. So that's where that comes from, right? So that's important. If I want to figure out v sub x, according to this, that's, or if I want to figure out delta x, that's my goal, I would use this equation. Delta x is change in velocity, which is v sub x, 3 meters per second, times time. But I don't know the time. Time isn't given to me. So, oh man, that sucks. I need to figure out time, right? Oh man, that's important. So the lesson goes on to give you a list of what are known as kinematic equations. And essentially, kinematic equations are just rearrangements of the velocity equation or the acceleration equation, or a combination of the two. So you know that velocity is displacement divided by time. You know that acceleration is velocity divided by time. So acceleration is really change in displacement divided by time again. So you can really kind of rearrange all of that to create a bunch of different formulas. And that's what these are here. So this is a nice table to have handy, and you might want to make a copy of this or a screenshot of this to have with you to always have as a reference. So one of the things that the lesson does that I'm not particularly fond of is uses these little arrows here to indicate that, right here, you can see that, to indicate that they're vectors. And I just don't like them because personally I think it's a little bit messy, makes things, just a harder thing to write. And you should know that velocity is a vector. You should know that acceleration is a vector. So it's not necessarily needed to write them if you know them. That's the case. So I don't think you really need to write that. Just know what that means, I guess. And going forward, you don't need to have that written in there to be correct. So they give you a whole table of kinematics, and it works very well. The other thing I liked about the book is that they've simplified these kinematics for specifically, in this case, projectiles launched at a horizontal, and they've divided them up into the y components and the x components, which is pretty nice to have when especially when you're kind of new to this. So I like this. I'm providing this to you as kind of an alternative view to hopefully help it make more sense. I'm going to also reference in the lesson to kind of show you how they are the same thing. But if you want to use this, take a screenshot of that, copy, paste it into a Word document, keep it in your notes. That might be helpful to you as well. So again, what we need is time. And when I go back to this in the book here and see which equations I can use to figure out time, I'm going to go to the remaining equations, which are all the y direction equations, and see which one of them, will help me figure out time. The first one, I need to have the y component of velocity, which I don't have. Just as a review, member, that when the orange first starts to fall, it has 0 y velocity. Instantaneously, right away, no velocity in the y direction. As gravity pulls on it, it gets faster and faster and faster. So the v sub yf is the final velocity of the orange when it hits the ground in the y direction, straight down, right? So I don't know what that is. So I can't use the first arrangement. Same thing with the second one. I don't know what that is. But the third one, I have all that information. I have the height of the table. That's my delta y. I know acceleration due to gravity, that's at negative 9.8 meters per second squared. I don't know time, but that's what I'm trying to solve for. So I can use this equation here to figure out the time. So what they have done is they've also done kind of the same thing. They have a similar equation, which is right here. It's pretty much the same, except if you notice, they are actually combining some things here, and they are, it just looks it's a little different. The second part of it here looks very much the same. The first part of it is missing on my end, right? So what they're saying is you can use this equation, and all you have to do is realize that the initial velocity, oh, I'm sorry, they're not using that equation. Which one are they using? They are using, um, okay, so they are using that equation, but they're doing it by components again, right? So we want to look at the y component and the x component. So we're using that equation for both. So, oh, I see what they're doing. I'm sorry. They're using this, they're not, they're just using the y component of this. So instead of using delta x here, they substitute delta y because you can do that and still use the same equation, which I think is a little unclear here. But they're basically using this equation here, but instead of solving for delta x, they're solving for delta y, which the equations are the same in either direction. And they're just making you realize that the initial velocity in the y direction is 0, so then you can just get rid of this. All the book did for us is they did that for us. They just simplified it for us. And they've already said you got rid of that part, that's okay. So I guess I like this part because it's already simplified. It's just a simplified version of this. This is the same here. Only again, we're using it in the y direction instead of in the x direction. And I think that's a bit unclear in there as well. But so we're going to use this bottom one. So for this bottom one, delta y is equal to 1/2 ay times t squared. All right. So we need to solve for t. So let me just rearrange some things here to solve for t. So delta y, okay. So I'm going to take y, and I'm going to take the 1/2 on the right, and I'm going to multiply by 2 to get rid of the 1/2 on the right. So I'm going to multiply both sides by 2, so that becomes 2y. I want to get rid of the ay on the right, so I'm going to divide by ay on the right. So that's going to go, I'm just going to short it to a because this is acceleration due to gravity. In fact, I can call it little g if you want to get technical. We'll just keep it as a. And then that gives us t squared. And then if I take the square root of both sides, that's going to give us t, right? So t is equal to the square root of 2y over ay. And that is exactly what they've done here, except for instead of putting the 2 in the numerator, they just divided by 1/2, which is the same thing. Mathematically the same thing. Okay. So when we do this, we take 2y, we have to remember, first of all, that y, I put 1 here, but I'm going to call that -1. Because even though the value is 1 meter, when I'm up on a tabletop, and this is my 0 at the top of the table, and the orange is falling 1 meter, it's going down -1. So that's why that is a -1 and not a +1. And the only reason why that matters is because if we didn't do that, we would have a negative value in the square root and it wouldn't work. So -1 times -9.8 meters per second squared, right? Times 2. So we're taking 2 times negative 9.8 meters per second squared, and we're dividing it. Oh, taking that back. We're taking 2 times negative 1, so that's negative 2. Let's just go ahead and do this here. Okay. So we have 2, and we're times it by a negative 1. We're dividing it by negative 9.8, and then we're taking the square root. And when we do that, we end up with that 0.45, which is the same thing they get in the lesson. 0.45 seconds. So that's our time. Once we have our time, then we can just go back and say, well, velocity times time is equal to distance. So 0.45 seconds times 3 gives us that 1.35 meters. So again, like I said, this set of kinematics is exactly the same as what I have here, but what I have here is dividing it, separating it by component. So you've got your y formulas, you've got your x formulas, and they're both simplified. So I think it makes it a little easier. So if you find that that is true, go ahead and use the ones I have this image for, just because I feel like it makes it a little bit more simplified. So that's pretty much it. You can use these kinematics to solve for any one of these variables. You can solve for time, you could solve for the height, you could solve for the final velocity. Any one of them works as long as you've got the other variables. And sometimes, more often than not, you have to use 2 different equations in order to be able to get at the answer that you want, because you have to use one equation to solve for a variable that you're missing, and then use a second equation to solve for the answer that you're looking for. Hopefully that helps, and hopefully it makes some sense. I'm hoping that this image maybe provides a little bit more clarity as well. And if you have any questions, let me know. And again, as always, come to class on Friday, and we'll go through some more sample problems like this. Have a great day, everyone.